Swayam Prabha. Digital India. Educated India.
Welcome. So in the last couple of lectures we have been looking at approximation algorithms. So let's briefly summarize what are the algorithms we have seen so far, what are the approximation algorithms. So we have seen a two approximation algorithm. For vertex cover, we have seen a 7/8 randomized approximation algorithm. For max 3 set, we also de-randomized it using method of conditional expectation. Then we have seen a half factor approximation algorithm, approximation randomized algorithm. For max cut, we de-randomized it using method of conditional expectation. Then we have seen 3/2 factor approximation algorithm. For metric TSP, which is a version of traveling salesman problem where triangle inequality is satisfied. Then we have seen big O of log n factor approximation algorithm for set cover problem. So all these algorithms are, the design does not follow a systematic approach. Each algorithm needs a new idea, and but one sort of high level idea is for minimization problems. The first step for an approximation algorithm, so to say, is the first step is to have a efficiently computable lower bound on opt. For example, the lower bound that we have used for vertex covered is matching. So the size of a maximal matching is a lower bound on vertex cover. Then for a traveling salesman tour, we have used two lower bounds. The cost of an MST, minimum spanning tree, and the cost of minimum matching and twice the cost of minimum matching, both are lower bounds on the cost of optimal tour, optimal TSP tour. Okay, good. But what is the lower bound for set covered, using which we have derived that big O of log n time algorithm? What is the lower bound used in the big O of log n factor approximation algorithm for set cover. So we'll see that that a lower bound for this problem comes actually from what is called a linear program, and not only that, that linear programming framework allows us to systematically come up with lower bounds on any optimization problem. So our next topic is on linear programming based approximation algorithms, and those sort of algorithms will be much more systematic than these approximation algorithms that we have seen so far. These algorithms are sort of look like an ad hoc, and each algorithm needs sort of a new idea. So we will the next topic that we will look at is linear program based approximation algorithm. So to look at this, so let us briefly discuss what is a linear program. So linear program. Now linear program, or LP in short, LP is an optimization problem where we have a set of variables and the goal is to optimize a linear function of these variables subject to a set of linear constraints okay. So for example, minimize say 7x1 plus x2 plus 5x3 subject to x1 minus x2 plus 3x3 is greater than equal to 10. 5x1 plus 2x2 minus x3 is greater than equal to 6, and x1, x2, x3 this is greater than equal to 0. So, this is the linear optimization for objective function which we want to maximize in this case, and these are the linear constraints. This is linear objective function, and this is a set of linear constraints. So, given such a linear program, one is interested to find interesting lower bounds. So, lower bounds on the optimization of the optimum value. So, let the optimal value be LP opt. How can we get some interesting lower bound on LP opt? For that, we can multiply these constraints with some number and then try to maximize this. For example, suppose let me multiply this first inequality with y1 and second inequality with y2. Then what do I get? I get y1 plus 5 y2 times x1 plus minus y1 plus 2 y2 times x2 plus 3 y1 minus y2 times x3. This is greater than equal to 10 y1 plus 6 y2. And what was my objective function? My objective function was 7 x1 plus x2 plus 5 x3. So, this was my objective function. So, now if it happens that y1 plus 5 y2 is less than equal to 7, minus y1 plus 2 y2 is less than equal to 1, it means the coefficient of x1 here is less than equal to coefficient of x1 here, and coefficient of x2 here is less than equal to coefficient of x2 which is 1, and coefficient of x3 is less than or equal to coefficient of x3 here. If this happens, then we can write 7x1 plus x2 plus 5x3 is greater than or equal to y1 plus 5y2 times x1 plus minus y1 plus 2y2 times x2 plus 3y1 minus y2 times x3, but this is greater than or equal to 10y1 plus y2. Okay. So, for each combination of y1, y2 which satisfies these constraints, these three constraints, gives us a lower bound. The corresponding y1 10 y1 plus 6 y2 is a lower bound on opt. The opt is must be at least 10 y1 plus y2. Now, which will be the strongest lower bound? The corresponding y1 and y2 which will maximize this. So, to get the strongest, which basically means largest, lower bound on LP opt, we need to solve the following linear program. We want to get a strongest lower bound, that means the largest lower bound. That is why I maximize 10 y1 plus y2. So, maximize 10 y1 plus y2 subject to, what are the constraints? 10 y1 plus 6 y2, sorry, here 10 y1 plus 6 y2. This is a lower bound only if all the three conditions in this box is satisfied. That means y1 plus 5 y2 is less than or equal to 7. Minus y1 plus 2 y2 is less than or equal to 1. And 3 y1 minus y2 is less than or equal to 5. And because we have multiplied these equations with y1 and y2 without changing the inequalities, that means y1 and y2 must be non-negative numbers. So, this program is called the dual linear program. Dual linear program of the initial linear program. The initial linear program is sometimes called the primal linear program. From the discussion, it is obvious that primal opt is greater than equal to dual opt. Is observation. And this is what is called the weak duality theorem, which we will formally state under certain conditions. So, this holds if and only if these linear programs, both these are not unbounded and it has a optimal solution. So, under normal circumstances, this is the condition which is basically called weak duality theorem. Okay, but not only that, we have stronger result that the duality theorem says that these two coincide. The optimal solution of dual is the same as the optimal solution of primal. So, here is, let me state theorem. This is called strong duality theorem. The primal program, the primal LP has a finite optimum if and only if the dual LP has a finite optimum in this case primal opt is equal to dual opt. So, this is the strong duality theorem, and we also have what is called a weak duality theorem, which simply follows from the construction of dual linear program. Weak duality if both primal LP and dual LP are feasible, then primal opt is greater than equal to dual opt. Okay, and also So, in the next class we will formally define duality and what is the standard form of a linear program, and then we will also show that dual of dual is a primal. Okay, so let's stop here today.